Okay, let's dive into this. Have you ever stopped to wonder how the seemingly random world around us, the rocks beneath your feet, the glass in your windows, or even the advanced electronics powering your smartphone, how all of that is actually governed by these elegant, perfectly predictable rules of geometry? Well, today, in this explainer, we're uncovering the microscopic architecture of ceramics. We're talking about the atomic Legos that build some of our world's absolute most fascinating materials.
So, here's our roadmap for the journey today. 1. Welcome to the ceramic world. 2. The rules of atomic packing. 3. Classic ceramic crystal structures. 4. The math of density. And finally, 5. Silicates, Earth's building blocks. We're going to build our understanding from simple rules right up to complex structures.
Section 1. Welcome to the ceramic world beyond traditional clay. Right off the bat, when you hear the word ceramic, your mind probably jumps straight to a potter's wheel or maybe a coffee mug. But we really need to dispel that myth right away. Formally speaking, ceramics are inorganic, non-metallic materials that are fired at extreme temperatures. And while traditional clay absolutely still matters, today's advanced ceramics literally form the backbone of the aerospace, computing, and telecommunications industries. It's so much more than just bricks and pottery.
Now, because ceramics combine at least two different elements, their atomic bonds actually exist on a spectrum. If you look at calcium fluoride at the top there, it's predominantly ionic, sitting at an 89% ionic character. But as we move down the list to something like silicon carbide, the bonds become almost completely covalent with only a 12% ionic character. And this spectrum is a real game changer because it fundamentally alters how these atoms pack together.
Section 2. The rules of atomic packing, the geometric balancing act of atoms.
We can actually think of crystallography as this giant microscopic geometric game. Because atoms, they don't just pile up randomly. They have strict requirements. So how do they actually decide to arrange themselves into a solid structure?
Well, for ionic ceramics, there are basically two golden rules to the game. Rule 1. Charge neutrality. The positive cations absolutely must perfectly balance out the negative anions. Rule 2. Size ratio. Because cations give up electrons, they're usually the smaller ones. So the relative sizes of these spherical atoms literally dictate how they can physically fit together in three-dimensional space.
Think of it like a Goldilocks scenario. That small blue cation wants as many nearest neighbor red anions around it as possible. But it's only stable if those surrounding anions physically touch the central cation. See, on the far left, the cation is perfectly snug, highly stable. In the middle, it's a bit of a tight fit, but it still works. But on the right, totally unstable. The anions are touching each other, sure, but that central cation is just rattling around inside. No way that holds up.
Because of this extremely strict geometric requirement, the exact mathematical ratio between the cation and anion radius literally dictates the destiny of the structure. A tiny ratio under 0.155 restricts the cation to having just two neighbors, creating a linear shape. But as the central atom grows, so does that coordination number. A ratio up to 0.414 yields a 4-coordinate tetrahedron. 0.732 gives us a 6-coordinate octahedron. And if the atoms are nearly identical in size, you get a perfect 8-coordinate cube.
Section 3. Classic ceramic crystal structures. Building the atomic Legos.
Now, what's really interesting about this is what happens when we start physically stacking these atoms. The larger, negatively charged anions pack very closely together in flat planes. And as these planes stack on top of each other, they naturally leave these tiny, empty pockets between them, which we call interstitial sites. Depending on the exact stacking pattern, these snug little pockets form either a 4-sided tetrahedral position or a 6-sided octahedral position for the smaller cations to slip into.
Let's look at a classic example here, the rock salt, or sodium chloride structure. This is an AX-type crystal, which just means there's a perfectly equal number of cations and anions. Notice how the green chlorine anions form this beautifully close-packed lattice, while the red sodium cations nestle perfectly into those 6-coordinate octahedral pockets. It creates this flawless, infinitely repeating geometric grid. And by just tweaking those radius ratios and electrical charges, we get a stunning diversity of structures. Rock salt gives us that 6-to-6 coordination. Zinc blende tightens things up to a 4-to-4 coordination. But check out the perovskite structure at the bottom, found in materials like barium titanate. It has a super complex ABX3 formula, and that's because it actually manages to seamlessly incorporate two completely different types of metallic cations into a single crystal lattice. It's absolutely brilliant.
Section 4. The math of density, proving the models in the real world.
Okay, so it's one thing to draw these beautiful, perfectly geometric models, right? But do they actually predict reality? The answer is a resounding yes. Using the theoretical density formula, if we just know the basic atomic weights, the geometry of the unit cell, and the ionic radii, we can calculate exactly how heavy a microscopic block of a given ceramic should be.
Let's actually run the numbers for a rock salt model. The math tells us the density should be exactly 2.14 grams per cubic centimeter. And this brilliantly illustrates our point, because when scientists go into a lab, take a real physical block of pure sodium chloride and weigh it, the experimental density is 2.16. That is just incredibly accurate. Our purely geometric, abstract math almost perfectly mirrors macroscopic reality.
Section 5. Silicates, Earth's building blocks. The geometry of the ground beneath us. Did you know silicon and oxygen are literally the two most abundant elements in the Earth's crust? That means the bulk of the actual ground beneath us is made of silicates. To understand them, we have to look at their foundational building block, the silicon-oxygen tetrahedron. As you can see, a tiny silicon atom sits squarely in the center, tightly bonded to 4 much larger oxygen atoms at the corners. And together, this little unit carries a net -4 charge.
But here's the catch. These tetrahedra don't just exist in isolation. Let's move to and see how this builds out. They actually share their corner oxygen atoms to build massive networks. On the left is a single unit cell of quartz. And on the right, you can see how those units connect to form a massive, highly regular, 3-dimensional network. This is crystalline silica. It's wonderfully ordered, yet surprisingly open, which is exactly what gives quartz its relatively low density. To ground all this abstract math, just look at macroscopic quartz crystals. Notice those sharp, angular geometric shapes? That natural shape, the one you can literally hold in your hand, is a direct, beautiful reflection of the microscopic atomic tetrahedral structure we were just looking at. The macro world perfectly mirrors the micro world. However, silicates don't always form perfect, flawless crystals. By adding what we call network modifiers, like sodium or calcium, we intentionally introduce impurities into the mix. And these modifiers literally break up the perfect network, lowering the melting point and creating a really high degree of atomic randomness. Actually, this transparent, disordered, non-crystalline chaos, that's the everyday glass we use in our windows and bottles.
So, we've journeyed all the way from strict, almost rigid mathematical rules to the stunning real-world structures of salts, crystals, and glass. So the next time you look through a window, or even just tap the glass on your smartphone, ask yourself, what invisible, elegant atomic geometry is silently at work holding the whole shebang together? Thanks for exploring this explainer with me.